Good morning, I am Sheetal from BSc Chemistry Honours second year. Today I am going to make an audio recording for visually impaired student of inorganic chemistry. Name of the chapter is Chemistry of Lanthanide element. We have learned that the element in which the last electron enters the f orbital of their atom are called f-block element. In these elements, the last electron is added to the third to the outermost called anti-penultimate energy level n-2f. These elements are called inner transition element because these constitute transition series. Within transition series d block elements, they consist of two series of elements placed at the bottom of the periodic table. These two series are formed by the filling of electron in 4f and 5f orbital and are called lanthanide and actinide respectively. The series involving the filling of 4f orbital following lanthanum element is called lanthanide series. The elements present in the series are called lanthanides. There are 14 elements in this series starting with cerium and ending with lutetium. The name lanthanide is derived from lanthanum, the first member of the series. These lanthanides are also sometimes referred to lanthanones. All these elements have closely similar properties and therefore are considered together. The reason for their similar properties is that the 4f orbital in which the electrons are added are embedded in the inner shell within 5, while 5d and 6s electrons which have similar configuration are exposed more to the surrounding. Because of their similar physical property, their separation and identification proved to be very difficult task. The first stage is their separation was to get them as oxide. However, the occurrence of the oxide of lanthanides was very rare. Therefore, these elements have also been called rare earth elements. Nowadays, the term rare earth is not used. Their substantial deposits occur in Scandinavia, USA, USSR, and India. General characteristics of lanthanide. The important general characteristics of lanthanide are discussed below. First, electronic structure and position in the periodic table. The lanthanide involves the gradual filling of 4f orbital. It may be noted that the energies of d orbital 5d and the next inner cell f orbital 4f are closely similar and therefore the order of filling the 4f orbital in the atom shows quite irregularities. At lanthanum, both 5d and 4f orbital become stable due to the increased effective nuclear charge as a result of poor shielding effect of 6s electron. Therefore, it is observed that at lanthanum, the incoming electron enters the 5d orbital and its electronic configuration is 5d16s2. However, as we move further after lanthanum, the energy of 4f subshell become lower than the 5d subshell and therefore the next electron in cerium enters the 4f subshell. The electronic configuration of cerium is 4f2 5d06s2. The filling of 4f orbital continue till we reach ytterbium in which the 4f subshell get completely filled and the electronic configuration of ytterbium is 4f146s2. Now after 6s and 4f subshell have been filled, the next electron goes to 5d subshell. The configuration of lutetium is 4f14 5d16s2. This constitute lanthanide. The general electronic configuration of lanthanide may be written as 4f0 to 14 5d0 to 16s2. Physical properties. The most important physical constant of lanthanide are given in table 2. These are discussed below. First is the ionization energy. The lanthanide has fairly low ionization energy. In general, the first and second ionization energy of lanthanide increase with increase in atomic number, but the variation is small and irregular. The variation of ionization energy with atomic number is shown in figure 1. It is clear from the figure that some deviation are observed in the regular increasing order such as for eurobium, gadolinium, ytterbium, and lutetium. These are attributed to stability of half-filled and completely filled F subshell. The first ionization energy are of the order 560 kJ per mole and the second ionization energy of the order 1150 kJ mole inverse. These values are quite comparable to alkali metals, especially calcium, whose first ionization energy is 589 kJ per mole and second is 1145 kJ per mole inverse. Second is melting and boiling point. Lanthanide have fairly high melting and boiling point. However, the melting and boiling point do not show any regular trend as we move from lanthanum to lutetium in series. Inspection of table 4.2 shows that europium and ytterbium have unexpectedly low melting and boiling point. These atoms from europium and ytterbium ions and result in weaker metallic bond because they are less than 3 electron per atom in the metallic bond. The other lanthanide atom gives 3 electron per atom in the metallic bond. Therefore, melting and boiling point of europium and ytterbium are low as compared to the value for the other lanthanide element. Third is density. The density of lanthanides are low, which range from 6.7 to 9.74 gram centimeter inverse cube. However, there is no definite trend in the density value of lanthanides with increase in atomic number. Europium and ytterbium have an expected low value. Fourth is heat of fusion and heat of vaporization. The heat of fusion and heat of vaporization also do not show definite trend with increase in atomic number. Fifth is electronegativity value. The electronegativity value of lanthanide between 1.0 to 1.15 are quite close to those of alkali and alkali earth metal as block element. Therefore, lanthanide are expected to form ionic compound. Sixth, electropositive character. Because of low ionization energy and electronegativity value, the lanthanide are electropositive like S block element. Oxidation state. The common oxidation state of all the lanthanide is +3. In addition, some lanthanide shows +2 and +4 oxidation state also. These are shown by those elements which by doing so attain the stable F0, F7, and F14 configuration. For example, cerium and Tb exhibits +4 oxidation state. Cerium and terbium attains F0 and F7 configuration respectively when they get +4 oxidation state as shown below. Second is europium and ytterbium +2 oxidation state. Europium and ytterbium get F7 and F14 configuration in +2 oxidation state as follows. LAGD and Lu exhibit only as +3 oxidation state. These elements show +3 oxidation state only because by losing 3 electrons, they acquire stable configuration of empty, half-filled and completely filled 4f subshell. Exceptional examples. Some other examples shows +2 +4 oxidation state even though they have electronic configuration other than F0, F7 and F14. For example, SM and TM shows +2 state having F6 and F13 electron respectively in which they have one electron less than half filled or completely filled configuration. Similarly, PRND and DY shows +4 oxidation state having F1, F2 and F8 electronic configuration. The stability of these usual oxidation state may depend upon some other thermodynamic and kinetic factors which are of significant importance, but these are less stable than +3 states, which is characteristics of the family. Color and spectral properties. The lanthanide are silvery white, but many lanthanide ions are colored, but both in the solid state and in the aqueous solution, the color remains same even on the change of an ion. Therefore, the colors are characteristics of the lanthanide ion. The color of the ion depends upon the number of unpaired electron because it has observed that ion containing NF electron have almost similar color of those with 14 minus NF electrons. Therefore, the different ion having NF and N14 minus NF are and their color are given in table 4. However, it has been observed that some Di and tetrapositive ions having same number of electrons, isoelectronic ions as positive ion do not have same color. For example, SM2 positive and europium 3 positive have same number of unpaired electrons, but they have different color. Some other example are given in table 5. The color of lanthanide ions arise due to absorption of light from the visible region of spectrum resulting in the electronic transition within the 4f levels FF transition. A remarkable characteristic of the spectra of tripositive lanthanide ion is that absorption bands are extremely sharp line-like bands in ultraviolet visible or near infrared region. Many of these bands are line-like and becoming even more narrower as the temperature is lower. This behavior is in contrast to absorption bands of DD transition which have broad absorption band. The band of lanthanide ion are so sharp that they are useful for characteristics the lanthanide ion. The main reason for every very sharp absorption band in the 4f orbital lies deep in the atom of the element. Therefore, they are effectively shielded from the surrounding by the overlapping 5s and 5p orbital, and consecutively the absorption band arises mainly from the electronic transition within the 4f level. Thus, the absorption band shows little dependence on the nature of the ligands. In addition to FF transition, sometimes color of lanthanide ion is also attributed to FT transition. The FF absorption transition of lanthanide ion have low intensity because they are not allowed, whereas FT transition are allowed. In contrast to FF transition, the FD transition are allowed and hence shows very intensive absorption band. For example, the FD transition observed for cerium 3 positive and Tb3 positive are very intense. Magnetic properties. All the lanthanide ion with the exception La3 positive, Lu3 positive, Ce4 positive and Yb2 positive ion are paramagnetic because they contain unpaired electron in their 4f subshell. The ions La3 positive, Lu3 positive, Ce4 positive and ytterbium 2 positive which have 4f0 and 4f14 electronic configuration are diamagnetic because they have no unpaired electron. The magnetic properties of lanthanide and different ion form from those of the transition element. As we know, the magnetic moment arises from two types of motion of the electron. The spin motion of the electron around its own axis produces magnetic moment called spin magnetic moment, while the orbital motion of electron around the nucleus produces magnetic moment called orbital magnetic moment. The observed magnetic moment of substance is due to the contribution of both the spin moment and orbital moment. In this case of transition element, the magnetic moment mainly corresponds to spin only magnetic moment. This is only due to the fact that d orbitals are not well shielded from the environment and take part in the bond formation with ligands. As a result, the d electron of metal interacts strongly with the ligands surrounding the metal ion. Due to the electric fields of the ligands, the orbital motion of electron gets restricted, thereby the orbital motion movement of these electrons get quenched. The magnetic moment of d block element thus arises mainly from the contribution of spin motion of the electron only. The spin only magnetic moment is given by mu spin only is equals to under the root n plus 2, where n is the number of unpaired electrons. The relationship gives almost correct values of magnetic moment for d block element. However, the above relationship is not valid in the case of f block element. In these elements, the 4f orbital are well shielded from the surrounding by the environment overlying 4s and 5p orbital. As a result, the electric field of the ligand surrounding the metal ions do not restrict the orbital motion of the electron. Thus, orbital contribution is not quenched. Therefore, the magnetic moment of lanthanide ion is due to the both electron spin and orbital motion of the electron. This may be calculated from the relation mu is equals to under the root 4s s plus 1 plus l plus 1, where s is the resultant spin quantum number and l is the resultant orbital moment quantum number. The theoretical and experimental observed magnetic moment value are given in table 6. The magnetic moment of lanthanide depend upon the atomic number and the number of unpaired electron. For the ion La3 positive, Gd3 positive and Lu3 positive, the magnetic moment correspond to spin only values. For these configurations, there is no orbital angular moment. It means L is equals to 0. The above expression becomes mu is equals to under the root 4s plus 1. And the magnetic moment may be calculated only on the basis of spin only value. Here S is equals to Ns, where N is the number of unpaired electron and S is the spin quantum number. 1 by 2, 4, 4f0, La3 positive and Lf4 positive. Lu3 positive configuration, there is no unpaired electron and N is 0 and their magnetic moment is also 0. For 4f7 configuration, the magnetic moment can be calculated on the basis of spin only value because orbital angular moment is 0. Number of unpaired electron n is equals to 7, s is equals to 1 by 2. S is equals to 7 into 1 by 2 is equals to 7 by 2. Mu is equals to under the root 16 is equals to 7.9 bm. This can be calculated as mu is equals to under the root nn plus 2. This gives 7.9 bm. The magnetic moment of tripositive lanthanide ions are plotted in figure 2. Lanthanide and lutetium are diamagnetic non-paired electron. It is observed that value increase up to neodymium and then decrease to 1.47 for Sm3 positive. It increases again in reaching a maximum value for dysprosium and holmium. Thereafter, it starts decreasing and becomes 0 for lutetium, which is diamagnetic. Occurrence of lanthanide. Although lanthanide were originally called rare element, the recent studies have shown that there are no rare. All the lanthanide except promethium occurs naturally. Some of them, particularly cerium, lanthanum, and neodymium, are very common and occur in fairly large quantities. Cerium is the 26th most abundant of all the elements. It has been observed that lanthanide having even atomic number are more abundant than their neighboring with odd atomic number. There are about 100 minerals known to contain lanthanide. The main minerals are monazite. It is the most abundant and most whispered minerals and accounts for about 78% of the lanthanide mine. It is the mixture containing La phosphates and trivalent phosphate of the lighter elements such as cerium, Pr, and D. It also contains small amounts of heavier element and thorium phosphates. This mineral is contaminated with other similarly concentrated minerals such as ilmenite and casterite. Monazite occur in southern India, South Africa, Brazil, Australia, Malaysia, etc. Bastinacite, it is mixed fluorocarbonate M3CO3F, where M is the lanthanide or lanthanide. The distribution of the metal in monazite and bastinites is almost similar, mainly cerium, lanthanum, Nd, and Pr, but the difference is that monazite contains around 5 to 10% THO twice and 3% ytterbium heavier lanthanide earths which are virtually absent in bastinacite. Large amount of bastinacite minerals are found in California, Sweden, New Mexico, etc. Cerite. It contains silicates of cerium, lanthanum, Pr, Nd, and Sm. It is also found in Norway and Sweden. In addition to about three main minerals, many other minerals in small amounts are. Method for separation into individual elements. The property of metal ion are determined by their size and charge. All the lanthanide ion are trivalent and have almost same size, so their property are almost identical. Therefore, the separation of lanthanide from one another is very difficult. Recently, method based on the repeated fractional crystallization, ion exchange technique, etc., which take advantage of slight difference or property like solubility, complex formation, hydration arising from very slight size differences of their trivalent ion have been used. These methods are discussed below. First is repeated fractional crystallization. Simple salt of lanthanide such as nitrate, sulfate, bromates, oxalates, as well as double salts like 2LaNO3 thrice dot 3 MgNO3 twice dot 24 H2O forms well-defined crystals. The solubility of these salts decreases from La to Lu, and therefore by repeating fractional crystallization number of times the individual component can be obtained. During fractional crystallization, the less soluble salts will be obtained first and the more soluble salt will be obtained last by atoll. By repeating crystallization process, the less soluble salt will be accumulated more and more in the crystal, and the mother liquor will contain more and more of the most stable salt. This method have been improved by use of the non-aqueous solvents such as ether. Fractional precipitation. When only a small amount of precipitating agent is added to a mixture of lanthanide salt, the substance having the lowest solubility product will be precipitate more rapidly and more completely. For example, if the sodium hydroxide is added to the solution of lanthanide nitrates, which is the weakest base and have the lowest solubility product, is precipitated, while the LuH thrice, which have the highest solubility product, is precipitated last. A partial separation takes place in the manner by dissolving the precipitate and then precipitating again. Number of times it is possible to have complete separation. Solvent extraction. The partition coefficient of the salt of these metals between water and organic solvent are slightly different. Therefore, these can be extracted by using different solvent and repeating extraction process again and again. For example, the partition coefficient of GdNO3 thrice between water and normal butyl alcohol is 1.06 times greater than that of LaNO3 thrice. This means that GdNO3 thrice can be separated from LaNO3 thrice by continuous extraction with water from a solution of the salt in butyl alcohol. Change of oxidation state. Some of the lanthanide shows +2 and +4 oxidation state in addition to the +3 states, which is most characteristics of all the lanthanide. The property of M2 positive and MF4 positive ions are different from those of the usual M3 positive ion. For example, cerium can be separated from mixture of trivalent ion of the lanthanide by oxidizing it to C4 positive state by reacting it with alkali KMnO4. C4 positive ion have been a greater charge than C3 positive ion, therefore it is smaller and less basic and less soluble. It can be precipitated as COH4 by the addition of small amount of an alkali, leaving all the trivalent lanthanide ions in the solution. Similarly, europium can be separated from mixture of trivalent lanthanide ion by reducing it first to +2 state by zinc amalgam. Then europium second can be precipitated as EuSO4, which is insoluble in water. The sulfates of all the trivalent lanthanide on the other hand are soluble in water and remain in the solution. Thermal decomposition. When mixture of lanthanide and nitrate is fused along with some alkali metals, nitrate at temperature is raised. When the least basic nitrate changed to oxide, therefore heavier nitrate decomposed first, while lighter lanthanide nitrate decomposed last of the all. Therefore, the process of decomposition of nitrites at different temperature is carried out, and the oxide separates at each stage are then dissolved in HNO3. Lanthanide compounds. The lanthanide are very soft and silvery white. They are electropositive and therefore they are reactive. They react with hydrogen forming the hydride of compound LnH2 and LnH3. These also react with several other known metals including oxygen, halogen, sulfur, nitrogen, phosphorus, carbon, silicon, etc. Most of the lanthanide compound are known in +3 oxidation state. However, some compound of lanthanide in +2 and +4 oxidation state are also known. The important lanthanide compounds are discussed below. Compound in +3 oxidation state. This is the most common oxidation state of lanthanide oxide. All the lanthanides tarnished readily in air. They burnt with oxygen forming the oxide Ln2O3. These are also obtained by ignition of hydroxide, carbonate, nitrate, etc. Ln2O3 are well characterized. Lanthanide oxides absorb water and carbon dioxide from the air to form the hydroxide and carbonate respectively. Therefore, the lanthanide oxides are strongly basic and their basic character decreases as atomic number increases. For example, La2O3 is strongly basic while LuO3 is least basic. The lighter, more basic resemble the oxide of group second alkali earth metal. All are soluble in water but absorb it to form hydroxide. They dissolve readily in aqueous acid to form solution which contain the LnH2OX3 positive ion, provided they are kept in the acid side of pH 5 to prevent hydrolysis. Hydrous hydroxides can be precipitated from this solution by the addition of ammonia or aqueous alkali. Ln2O3 adopts three types of structure. A type, this consists of LnO7 units which are approximate to kept octahedral geometry, they are favored by the highest lanthanide B types. These consist of LnO7 units which have been kept trigonal by prism and kept octahedron geometry which are favored by the middle lanthanide C type. These have fluoride structure in which one quarter of anions are removed in such a way so that reduce the metal coordination number from 8 to 6. These are favored by middle and heavy lanthanide. Hydroxide. The lanthanide reacts slowly with cold water but more rapidly on boiling with the liberation of hydrogen and form the corresponding lanthanide hydroxide. The hydroxide can be prepared by adding dilute solution of sodium hydroxide to solution containing lanthanide ions. The hydroxide are precipitated as gelatinous precipitates. These are ionic compound and are basic. Lanthanide hydroxide are less basic than CaOH twice but more basic than AlOH thrice, which is amphoteric. The basic character of lanthanide hydroxide decreases with the increase in atomic number along the series. Therefore, LaOH thrice is most basic while LuOH thrice is least basic due to the lanthanide contraction. Halides. Lanthanide in the oxidation state plus 3 form trihalide anhydrous lanthanide fluoride are prepared by adding HF4 NaF solution to the salt solution containing Ln3 positive ion. The fluoride are very insoluble and therefore are easily precipitated from their solution by HF4 NaF. However, with excess F negative, the fluoride or heavier lanthanide may form soluble complexes. Anhydrous lanthanide chloride are prepared by heating the metal in the atmosphere of dry chlorine or by heating lanthanide oxide with carbonyl chloride. The chloride are this liquescent, non-volatile solid. These are soluble in water and crystallize with 6 or 7 molecules of water of crystallization. It may be noted that simple anhydrous lanthanide halide cannot be prepared by simple heating and dehydrated salt as they form lanthanum oxochlorate instead of dehydrating to anhydrous halide. Anhydrous halide can also be prepared by heating the oxides with appropriate ammonia halide. The aqueous solution of other trihalides are prepared by dissolving the oxide or carbonates in aqueous HX and hydrated can be crystallized. Anhydrous trihalide can be prepared by thermal dehydration of these hydride of lighter lanthanide. The bromide and iodide are more susceptible to hydrolysis, and dehydration leads to contamination of oxohalide. Therefore, they are preferably prepared by direct combination. Nitrite. At higher temperature, the lanthanide react with nitrogen to give nitride of formula La, and it get hydrolysis by water like aluminium nitride ALN to give the corresponding hydroxide with the liberation of ammonia. Oxosalts of lanthanide. A large number of oxosalts of lanthanide are known. These include carbonates, nitrate, sulfate, oxalate, phosphates, and perchlorate. These are generally prepared by dissolving the lanthanide oxide, hydroxide, or carbonates in corresponding acid. For example, double salt of lanthanide. Lanthanide sulfate are known to form double salt with ammonium and alkali metal sulfates. Some common examples are: it may be noted that double salt in case of alum are generally associated with as many as 24 water molecule of crystallization. However, the double salt of lanthanide cannot be associated with as many as 24 water molecule of crystallization. This is because the lanthanide ions are too large to coordinate with 24 water molecule of crystallization octahedrally as in alum. Compound in plus 4 oxidation state. Among the lanthanide, only cerium, parasodium, and neodymium, terbium, and dysprosium shows plus 4 oxidation state. The only lanthanides which exhibit the plus 4 oxidation state in solution have aqueous chemistry is Ce4 positive. The Ce4 positive solution are extensively used as versatile oxidizing agent in volumetric analysis. Aqueous Ce4 positive solution can be prepared by oxidizing a Ce3 positive solution with strong oxidizing agents such as ammonium peroxide disulfate. Solutions are also used in organic reaction for the oxidation of alcohol, aldehyde, ketone, etc. The common compound in plus 4 oxidation state of cerium are CuO2 white when pure and CEO2 dot H2O dot, and ILO gelatinous precipitate. CO2 is insoluble in acid and alkalis but dissolved when reduced, giving C3 positive solution. The analogous dark colored PrO2 and TbO2 are obtained from their stable oxide Pr6O11. And major difference between the dihalide of europium and calcium is that the dihalide of europium have magnetic moment of 7.9 bm corresponding to 7 unpaired electron, whereas calcium correspond are diamagnetic. Uses of lanthanide. The pure metals have no specific uses and therefore these metals are extracted as a mixture of alloys. These are called mixed metal. The common uses of lanthanide and their salt are given below. Cerium constitutes about 30 to 50% of alloy of lanthanide. They are used for scavenging oxygen and sulfur from the other metal. Second is addition of about 3% of mixed metal to the magnesium increases its strength and is used in making jet engine parts. Third is steel mixed with LaCePr and Nd is used in the manufacture of flame throwing tanks. Fourth is lanthanide oxide are used for polishing glass. Neodymium and parasodium oxides are used for making colored glasses for goggles. These are particularly useful for glass bowlers as they absorb the bright yellow light. Fifth is cerium salt are used in dyeing cotton. They are also called as used as catalyst. Sixth is lanthanide compound are used as catalyst for hydrogenation, dehydrogenation, oxidation, and petroleum cracking. They are also used in magnetic and electric device for paramagnetic and ferromagnetic properties. Gadolinium sulfates, heptatitrate have been used to produce very low temperature. Recently, lanthanide have been used in lasers. For example, neodymium oxide dissolved in selenium cyclochloride can be used as powerful liquid laser. Cerium magnesium alloy are used in the flashlight powders.